Hi everybody, Dr. Carl here. I'm wanting to talk today about trig substitution. And what we're going to do is to take a couple of identities and work up some patterns from them that'll help us integrate things that we can't integrate any other way. So we'll see that a couple of identities go a really long way. Now, as always, I strongly recommend that you follow this video with paper and pencil in hand, and if I take a step that you're not following, pause the video, spend a little time working through that step as best you can, and if you're still having difficulty with it, make a note of the time in the video and get hold of me and we can work through it together in more detail. Alright, so let's take a look at some of these things. Basically, there are going to be three patterns that we get from two identities. And the first identity is one you should remember pretty well from trigonometry. Sine squared theta plus cosine squared theta equals 1, the circle identity. And what I'm going to do with this, in order to make it more useful, is I'm going to subtract sine squared theta from each side, and I'm going to wind up with cosine squared theta equals 1 minus sine squared theta. So the pattern we're going to be working with from this is 1 minus something that's squared. And whenever there's that something being squared that's subtracted from 1, you'll be able to replace that something with the sine of theta. As a result, then I'll be able to replace the whole expression, 1 minus sine squared theta, with cosine squared theta. And that'll make things simpler and easier to work with. Trust me on this, we'll see how it works in just a minute. The other trig identity I wanted to work with is tangent squared theta plus 1 equals secant squared theta. Now, you may have a little difficulty remembering this one. I always did, until I realized that I could remember it more easily by thinking of it as the first identity divided through by cosine. If I take sine squared theta and divide it by cosine squared theta, I'll get tangent squared theta. And then the second term, cosine squared theta, also divided by cosine squared theta, is just 1. And on the right hand side, 1 divided by cosine squared theta is secant squared theta. So it's really just another version of the same identity. So this identity is going to help me with a slightly different pattern. That's when I have something squared plus 1. Or, on the other hand, I could have 1 plus something squared. They're the same thing. And in this case, when I have this sort of a pattern, I can replace that something with the tangent of theta, giving me tangent squared theta plus 1, or 1 plus tangent squared theta, and that gives me the secant squared of theta. Now the third pattern comes from this identity also. If I just take the 1 and subtract it to the other side, I get tangent squared theta equals secant squared theta minus 1. And this will give me the pattern something squared theta minus 1. Whenever I have this kind of a pattern, I can replace that something with the secant of theta and then swap all of secant squared theta minus 1 with tangent squared theta, and it makes things easier. It really does. Alright, let's see how this works. We definitely need an example. Now, these do get kind of involved. Some are more involved than others. The first one, I wanted to show you some of the details on how it works. Essentially, it works in 3 stages. And those stages are doing the substitution, doing the integral, and then changing everything back from the substitution. So let's see how this works. Our integral is the integral of the square root of 1 minus x squared dx. And what I'm going to do, of course, the thing that's being squared is the x, 1 minus something squared. The first thing to realize is that this integrand is not 1 minus x. I know that's tempting. Believe me, I know. But if I could just break a square root up like this, life would be a lot easier. If you think about it with some numbers like 9 and 4, right? If you think of 9 minus 4, that's 5. So the square root of 9 minus 4 is the square root of 5, right? But the square root of 9 is 3, and the square root of 4 is 2, and 3 minus 2 is 1. Now the square root of 5 and 1 are not the same thing, which is why the square root of 1 minus x squared and 1 minus x aren't the same thing. So we can't break it up that way. We're stuck with this pattern. U substitution, plain old substitution, doesn't work on this. If I tried to make u equal what's under the square root, 1 minus x squared, I would still need to worry about du, which is a 2x dx, and although minus 2x dx rather, and although you can always play around with the constants, I can't put an x in out of nowhere to work with the differential. So I don't have another way to do this one, and that's why I take a few moments and remember that trig identity, 1 minus something squared. I'm going to let that something, that x that's being squared, be the sine of theta. Now if I do that, I do, like with a regular substitution, have to worry about the differential. I have to take the derivative of both sides and realize that dx is going to be the cosine of theta d theta. So I'll do both of these replacements. The x that's being squared is going to become a sine theta, and the dx at the end becomes cosine theta d theta. So if I swap all those out, I get the square root of 1 minus sine squared theta times cosine theta d theta. Now what's nice about this is I can replace the 1 minus sine squared theta with cosine squared theta. So I've got the square root of cosine squared theta. That's the square root of something squared. And that's really nice. This is where it becomes really helpful, because a square root and a square will cancel each other out and simplify, and I've just got the cosine of theta times the cosine of theta. Cosine squared theta d theta. That's my integral. That's another way to write it. Now you may be thinking to yourself, well, geez, this involves trig functions. It's not really that much easier. But the thing is, I have gotten rid of the square root, and I have gotten rid of one function inside another. It's just cosine being squared. It's much simpler to work with, and this is one of the trig integral patterns that you've worked with before. So let's take a look at how to integrate this. We're going to crank through it. It's time to actually integrate it now that we've done the substitution. And now you may remember when you're dealing with powers of trig functions, there are a couple of different patterns. Alright, there are a lot of different patterns. But one of the easier ones was that whenever we have an even power of cosine or sine, we go ahead and use the half angle formula for that trig function in order to do the integral. Now if you're having trouble remembering the half angle formulas, that's alright. You can look it up real quick and refresh yourself. You may remember it has square roots in it, and that's why it's nice for working with trig functions that are being squared, cosine or sine, when they're being squared. So the half angle formula will give us this replacement. We have the integral of 1 plus cosine 2 theta over 2 d theta. And again, look up the half angle formula, see how that works for yourself. One of the things I'm going to do with this to make my life a little bit easier is take that 2 in the denominator out front as a 1/2. Makes life a little easier. Then I'm just integrating 1 plus the cosine of 2 theta d theta. Now integrating 1 isn't bad, right? And if you're thinking the integral of 1 is just x, you're really close, except that for this one we're not working with x's, we're working with theta. D theta is my variable. Theta is my variable, so when I integrate 1 I'll get theta, not x. I also have to integrate cosine of 2 theta, and cosine of 2 theta is a little different than cosine of theta. You have to do a quick substitution, a plain old u substitution for 2 theta. And when we do that, if you let u be the 2 theta, of course the differential, you need du to be 2d theta. I don't have a 2d theta in here, so I'll divide both sides and I'll say du over 2 equals d theta. So now I'll replace this and I'll get cosine of u, and replacing the d theta gives me du over 2. It's an extra 1/2 factor, a 2 in the denominator. So I'll go ahead and replace these, but the integral of cosine is just the sine function. So that's not too bad. What I wind up with then is 1/2 out front. The integral of 1 is theta, and the integral of cosine of 2 theta is sine of 2 theta divided by 2. We get that 2 in the denominator from the differential terms. And that's plus c. I've integrated. I'm done. This is cool, isn't it? I mean, I was able to turn my one integration pattern into a different integration pattern, a trig integration, and do the integral. But we're not really done yet. I'm sorry. Here's that integral we came up with. And here's the problem with it. My original function that I was integrating was all in terms of the variable x, wasn't it? This is all in terms of a different variable, theta. So it's not really the antiderivative of the function I started with. What I need to do is change everything back to being in terms of x. And this is the third stage, right? The first stage was doing the substitution. The second stage was taking that trig integral and integrating it. This is the third stage, changing everything back in terms of x. Now, it may seem pretty ugly, but it's not that bad. See, we had one really nice tool. We had the substitution. X was equal to the sine of theta. And that means that this theta up here, that's sitting there by itself, can be thought of as the inverse sine of x. And we could just replace that right out. It's very straightforward. And we get the inverse sine of x. Now that takes care of the first term. But then there's that second term, the sine of 2 theta over 2. We had let x be the sine of theta, but that's not the same thing as the sine of 2 theta. And if you're thinking, oh, we can cancel the 2's, you need to be a little more careful. Sine of 2 theta, you can't just pull the 2 out front. It's tempting, sort of like that whole square root of 1 minus x squared being 1 minus x. It's not true. Think about it with an angle for a moment. The sine of 90 degrees is 1, but the sine of double that, 180 degrees, is 0. It's not 2 times 1. You can't just pull the 2 out. So what do we do? And actually, it's that idea of doubling the angle. There are these wonderful double angle formulas you might remember, and the one for sine says that the sine of 2 theta is 2 sine theta times cosine theta. So I'm going to replace that. And what's really nice about this is that that 2 out front does cancel with the 2 in the denominator. So what I wind up with is this inverse sine of x for the first term, and now I've got sine theta times cosine theta for the second term. Half times all that plus c, right, because I integrated. And I know what the sine theta is, right? We've got that right up here. The sine theta equals x. So I can replace that right away. That part's just an x. The question is, what about the cosine of theta? How's that going to work? Well, what I can work with then is that circle identity again. Sine squared theta plus cosine squared theta equals 1, or cosine squared theta is 1 minus sine squared theta. And you may be thinking to yourself, but I don't have a cosine squared theta. I only have a cosine. That's okay. You could take a square root. The cosine theta is the square root of 1 minus sine squared theta. And swapping sine back for x, I get the square root of 1 minus x squared. Now this is something that happens in a lot of these trig substitution integrals, is that you wind up with the exact same pattern somewhere in there that we started with. It kind of makes sense because remember, we're basing this on the derivative of a function. We're taking an antiderivative. So it makes sense that part of the function, part of the result at least, will look like the function we started with. So if I make these substitutions, put in the x for sine theta and square root of 1 minus x squared for cosine squared theta, I wind up with my antiderivative, and now it's been completely transformed in terms of x. It is 1/2 times the quantity inverse sine of x plus x times the square root of 1 minus x squared. Of course, plus a constant at the end that might have been there. And the one thing I need to recommend you do is take a few minutes, and you could pause the video and do it right now if you like, but check this antiderivative, check this integral by taking a derivative, right? We know the derivative pattern for the inverse sine function, and you use the product rule on x times that square root, and you need the chain rule for the square root part. And once you do all that, you'll have a bunch of terms, and if you get common denominators on them and put them all together, you'll find out that you actually get the square root of 1 minus x squared, the function we started with. This is always the best tool you have to check an integral, is to take its derivative and see that it actually works. Alright, I want to do another example for you though. There were 2 other trig patterns. I'm going to do 2 more examples, one of each, and they're also going to show you some of the ins and outs of working with trig substitutions in general. So let's take another example. This one goes pretty quickly though. It's not bad at all. We'll do the integral of 3 over 1 plus 4x squared, and you may be thinking to yourself, oh, what? I can do that, right? It's 3 over 1 plus 3 over 4x squared. You play around with that. Well, be careful. Just like square roots not breaking up, you can't break division up over addition in the denominator. And if I try to use substitution thinking I could make, well, I'll make it 3 over u, right? Again, I don't have an 8x dx for my differential. I don't have an x in order to put in my differential. So this isn't going to work unless we take a squared term in the bottom and use that pattern of 1 plus something squared. That was my second pattern, you might remember, involving the tangent and the secant. Well, I need to know what that something squared is, and what's being squared in this case is 2x. So be careful with these, right? It's not just the x that's being squared, it's 2x being squared to get 4x squared. And by the way, if the bottom were something like 1 plus 5x squared, then I'd replace the square root of 5 times x, because that's what would be being squared. So sometimes the constants can get a little ugly. This one's not too bad though. I'm going to replace 2x with the tangent of theta. So that 2x that's being squared down there is going to be replaced with the tangent of theta. That's my substitution. And of course I need the differential. I need 2 times dx, the derivative of the left side, being equal to the derivative of tangent, secant squared theta d theta. Alright, so there are my substitutions, more or less. I don't have a 2 dx. I'm going to go ahead and divide through by 2. So dx is secant squared theta d theta over 2. And when I put these in, I'll have a 1 plus tangent squared on the bottom. And on the top, I've got that 3. I'm going to go ahead and pull the 3 out. And I'll have secant squared theta d theta over 2. And I'm going to go ahead and pull the 2 from the denominator out also. Now, this is the sort of thing with constants that after a little while, after a little practice, you can do in your head practically. You can do them pretty well. Again, if you're having a little trouble, just do the substitution and then see. You'll be able to pull out a 3 from the top and a 2 from the bottom. It works pretty well. And what I've got left is secant squared theta on top, and on the bottom, 1 plus tangent squared theta. But the whole idea of doing this is that the identity pattern for 1 plus tangent squared theta gives me secant squared theta on top and secant squared theta on the bottom when I use that identity. And of course, secant squared theta over secant squared theta is just 1. I'm integrating 1. That's my whole integral after trig substitution. That really did simplify things a lot, didn't it? So when I integrate 1 d theta, I just get theta. So I get 3 halves of theta plus c, and then I have to go back. And remember, 2x was equal to the tangent of theta. And that means that theta by itself is just the inverse tangent of 2x. Don't forget the 2, right? It's the inverse tangent of that whole thing, 2x. So I get 3 halves times the inverse tangent of 2x plus a constant. And you may have recognized this sort of thing already as the derivative of an inverse tangent, right? The derivative of inverse tangent of x is 1 over 1 plus x squared. From way back, right, when we did the inverse trig functions a little while ago. Long while ago, depends on when you did it. But that's the result. That's it. There are 3 stages again, remember. First we do the substitution, which we did. 2x was tangent theta, and we did the differential. Then we did the integral, and this integral was a real easy one, integrate 1. And then we changed back from theta back to the x variables. And in this case, again, it involved an inverse trig function. That's okay. Check it with the derivative. It works great. All right, I got one more example for you. This is going to involve the third pattern. It's also going to involve a little bit more in the substitution. So let's take a look at this one. This is e to the x on top. Oh boy, exponentials. E to the x on top, and on the bottom we've got e to the 2x minus 16, whole thing raised to the 3/2 power. And again, if you try to do a u substitution, it's not going to work. You can try, but it's not going to work out for us. We're going to wind up with something that says u squared minus 16 down inside that 3/2 power. And your first reaction after seeing that, after saying u substitution, your first reaction is going to be, wait a minute. My patterns were 1 minus something squared, 1 plus something squared, or something squared minus 1. This is not something squared minus 1, is it? This is something squared minus 16. Well, that's all right. What we can do is factor the 16 out. And you may be saying, how can you factor out a 16? It's only in one of the two terms. You can only factor things out that are in both terms. Well, how about if I write that first term as 16 times e to the 2x divided by 16? If I play around with it a little bit, put in what I need, factor out the 16. What I'm going to get then is e to the 2x over 16 minus 1 inside those parentheses, all raised to the 3/2. Now, the other thing is, the 16 I took out was also raised to the 3/2 power. And if you take 16 to the 3/2 power, that's right, the half part is a square root. Square root of 16 is 4, raise 4 to the 3rd power, you get 64. So that's where that 1/64th out front came from. That's the 16 in the bottom that I factored out. It becomes a 64 in the bottom. I've just pulled it out front to get it out of the way. Again, take a few minutes, paper and pencil, convince yourself that this is exactly the same integral. It really is. Okay, now the question becomes, what's being squared? Okay, what's being squared here? Remember, e to the 2x is just e to the x being squared. That's how I recognized I would need this pattern. But it's also over 16, which is 4 being squared. So what's really being squared here is e to the x over 4. That's what I'm going to replace with my trig function. And which trig function is it? Well, for something squared minus 1, I need to use that second identity and replace the squared item with the secant. So it's secant squared minus 1. Alright, so I'm going to let e to the x over 4 be the secant of theta. And when I let e to the x over 4 be secant of theta, of course I have to take the differential. The derivative of e to the x is just e to the x. The derivative of e to the x over 4, the constant just hangs around, is e to the x over 4. So on the left of my differential, I get e to the x over 4 dx. And on the right side, I get secant theta tangent theta d theta. The derivative of secant is secant tangent. Alright, I don't have an over 4, but that's okay. I've got e to the x dx, and I'll just multiply through by 4. So I'll replace e to the x dx, that's on top of my original integral, with 4 secant theta tangent theta d theta. And of course, the 4, the constant 4, I can pull out front. Right? So I've got 1/64th. I've got my 4 secant theta tangent theta d theta as a replacement for dx, for e to the x dx. And on the bottom, I've got secant squared theta minus 1, and that's going to be really helpful. I'm going to go ahead and pull the 4 out front, and we can also replace secant squared theta minus 1 with tangent squared theta. That's the entire point of this integral, right? That's the entire point of doing this substitution, is to replace that pattern with something, tangent squared in this case, that I can easily raise to the 3/2 power. And when I do, well, let's see, the 4 and the 64 cancel down a little bit. That's just 1/16th out front. And tangent squared, when you raise it to the 3/2 power, cancels down to tangent cubed. So I've got a secant tangent on top and a tangent cubed on the bottom. One of the tangents will cancel. And again, the cancellation is the best part about all this. So I wind up with an integral 1/16th secant theta on top, tangent squared theta on the bottom d theta. A trig integral. And believe me, even this looks a lot better than the original did, with all those exponentials and the things raised to the 3/2 and all that stuff, right? It's just powers of tangents and secants. And you may remember working with powers of tangents and secants from doing trig integration, but this one's a little bit different. So let's go ahead and do this integral. 1/16th, the integral of secant theta over tangent squared theta d theta. And it's tempting to try and do just a substitution, right? You let u be secant, its derivative. No, derivative of secant is secant tangent. Derivative of tangent is secant squared. That doesn't work either. Well, you may remember that some trig integrals are much easier to do if you actually convert them back into sines and cosines. So if we change the functions back, if we take secant, which is 1 over cosine, and tangent, which is sine over cosine, and make those changes, I get 1 over cosine on top instead of the secant, sine squared theta over cosine squared theta on the bottom instead of tangent squared, and then I can flip and multiply. And what's nice about this is that when I flip that bottom fraction up, I get cosine squared over sine squared, and the cosine that's on top cancels with the cosine in the bottom. So in the end of it all, and again, take a second and make sure this works when you flip and multiply and do the cancellation, I wind up with 1/16 cosine theta on top, sine squared theta on the bottom. And this one I could do with a substitution pretty nicely. If you let u be the sine of theta, the function on the bottom that's being squared, I'll have u squared on the bottom, and its differential, its derivative, du is cosine theta d theta, which is exactly what I've got on top. So I'll replace cosine theta d theta with du, and I'll replace sine theta with u, and I'll wind up with 1/16 out front still, and the integral of 1 over u squared d theta, and remember that's easier to do as a negative power. 1/16 times the integral of u to the minus 2. You add 1 to the power, it's u to the minus 1, divide by minus 1, you get 1/16 negative u to the minus 1 power, plus a constant. I've done my integral, right? It's in terms of u though, but I know what u is. U is the sine of theta. So I get negative 1 over 16u plus c. That's negative 1 over 16 sine theta plus c. That looks pretty good. I've integrated. Oh, wait. I had it in terms of u. I put it back in terms of theta. That's nice. But my original function was in terms of x. I still need to swap theta back in terms of x. And that's the third step for any of these trig substitution problems, right? So we did the first step on the last slide where we substituted and simplified. And we got this integral. We've integrated it now. Now what we need to do is change it back in terms of x. Now I'm going to use a different technique for this. What you might remember is that the substitution we did involved e to the x and the secant of theta. And what I've got here is the sine of theta. And that's kind of hard to relate to the secant. So somehow we need to get back to x. I'm going to use a technique that's called the triangle method. And this can be used with any trig substitution we have. I could have used it on the first one. It wouldn't have been much help on the second one. But it's most helpful when you're trying to change from one type of trig function to another. On the first one I had to change from a sine theta in my substitution to a cosine theta that showed up in my integral. I was able to do that with an identity, but I could have used this triangle method. So the triangle method takes the substitution we did and makes a right triangle that has the appropriate sides. In this case, the substitution we did was e to the x over 4 was equal to the secant of theta. Now, I know that sine is opposite over hypotenuse on a triangle, and the cosine of theta is adjacent over hypotenuse, and the tangent of theta is opposite over adjacent, right? However you remember those, whether it's SOHCAHTOA or any of those other memory devices. You may not remember secant all that well. It turns out to be hypotenuse over adjacent, but that's okay because secant is 1 over the cosine. So if I say e to the x over 4 is 1 over the cosine, I can actually just flip both sides of this equation, it'll still be equal, that the cosine of theta is 4 over e to the x. And that tells me, right, from a right triangle that I'm working with an angle of theta, the cosine theta, remember, is adjacent over hypotenuse. That means that my adjacent side is the 4 that's on top, and my hypotenuse must be e to the x, what's on the bottom. So the cosine of theta is 4 over e to the x, tells me how this triangle is set up. Well, that's okay, except I'm missing a side, right? I'm going to call it b, because remember a squared plus b squared equals c squared, Pythagorean theorem. What Pythagoras tells us is that 4 squared, a squared, plus b squared equals c squared, e to the x quantity squared. And what I need to know is b, because you remember my integral had a sine in it, which means I'll need opposite over hypotenuse for the sine. So I need to solve this for b, and again, you just subtract the 4 squared over to the other side, and you get b squared is e to the x squared minus 4 squared, and now I can take a square root to figure out what b is. And of course, e to the x squared can also be written as e to the 2x. It could be simplified. 4 squared is just 16. So b is the square root of e to the 2x minus 16. And you remember what I said about the pattern you used in your substitution? The pattern in the original integral showing up again? Well, here it is, right? E to the 2x, something squared minus, well, but it wasn't minus 1, right? It was minus 16. It shows up, and it shows up as side b. That means that sine theta is actually this square root term, e to the 2x over 16 minus 16 over e to the x, opposite over hypotenuse, b over e to the x. That's my sine theta. Now if you go back to the original integral, it was on the previous slide, and I'll make these slides available and you can review through them. It's a little easier sometimes than sitting through the whole video and listening to my lovely voice again. But the sine theta is this square root of e to the 2x minus 16 over e to the x. In my original integral, I had minus 1 over 16 sine theta. That's minus 1 over 16 times this mass, right? E to the 2x over minus 16 under a square root divided by e to the x. And since it's in the denominator, I can flip and multiply and simplify it a little bit more. And I get negative e to the x divided by 16 times the square root of e to the 2x minus 16. This whole thing. And it's ugly, no two ways about it, but the integration itself wasn't that bad, was it? Because we changed things into trig functions. Again, as always, I strongly recommend you take this result and take its derivative and make sure that you get back the trig function that you started with. I'm sorry, not the trig function, the original function in terms of e to the x that you started with. And you can almost see, right, we're going to need the quotient rule here, the chain rule for the bottom. There's going to be a minus 1/16 hanging around. But we have something to the 1/2 in the bottom, and you know darn well that taking the derivative of a negative 1/2 power gives you a negative 3/2 power. And didn't we have e to the 2x minus 16 to the 3/2 in the denominator of the original? You can almost see that the derivative is going to work out and give us back our original problem. So I strongly recommend you take that. Let's recap real quick here. So we had three patterns. They were 1 minus something squared, and in that case you use the sine of theta as your replacement. Something squared plus 1, or 1 plus something squared. In that case you use tangent theta as your replacement. And something squared minus 1, and in that case you use secant theta as your replacement. Now, no matter which pattern you did use, you're going to wind up with a trigonometric integral, an integral involving trig functions. You are going to have to deal with some constants sometimes, like we did, having to deal with that 16, right? You deal with the constants as you need to deal with them to make the substitution work. You're going to wind up with a trig integral. You do the trig integral, and I know that sounds easy. Some trig integrals are pretty straightforward. Some of them take a while. But you do the trig integral, and then when you're done, you change back to the original variables. And if you have to swap trig functions from one to another, if you're not working with the original trig functions you did in your substitution, then you should really use the triangle method. Practice that on all your trig substitutions. Practice making that triangle, and you can make it as soon as you make the substitution, right? By the way, for some simpler substitutions, remember we had one that was like 2x equal the tangent of theta? And you say, well, tangent theta is opposite over adjacent, right? Well, think of 2x as 2x over 1, right? Because then you'll have 2x for one side, 1 for another, and it'll be 4x squared plus 1, which showed up in the pattern as the a squared plus b squared term. So these things do work. The triangle method will work with any trig substitution. As soon as you make the substitution, try setting up the triangle just to get the practice. And that's it. That's trig substitution. I think I've hit pretty much, well, I hit all three patterns, right? And I hit just about every kind of quirk you can get with actually substituting the trig functions, as far as replacing other functions with trig functions or dealing with the constants. So it's not a simple method, I'll give you that. It's not a simple method, but there are essentially three steps: recognizing the pattern and replacing it, getting a trig integral, and doing the trig integral is the second step, which can be a very long step, and then changing back to the original variables when you're done. That's always the third step. And don't forget, whenever you do any kind of integration, check it by taking the derivative, just to make sure you didn't lose something somewhere, because it's real easy to lose a constant. You got a 1/2 or 1/16 sitting out front, and you forget it for a few minutes, and then you forget to put it back, right? That's easy to do. So watch out for things like that. I'll see you next time. Again, I'll make these slides available so you can review them anytime, and get hold of me if you have any other questions. let's put it this way. Get hold of me when you have other questions. It's not a matter of if, is it? This stuff is not easy, and but with practice, you get more familiar with it. And like any hard path, every time you do it makes it a little easier. I'll see you all next time. Bye bye.